Welcome, everyone, to this webinar led by the IEA MSD Technical Committee. I'm Steve Fisher, the MSD Technical Committee Chair, and facilitating this workshop on behalf of myself and Erwin Spekla, my MSD Technical Committee Co-Chair. Very excited today to have with us Dr. Woojin Park from the Life Enhancing Technology Laboratory, Department of Industrial Engineering at Seoul National University. Really excited to have Woojin here today for two reasons. One, to share some of his research, which you can see the title on the screen, and to get a bit of an update around the IEA 2024 Congress in Jeju, which I know Woojin will share some updates with us at the end of the presentation. So really looking forward to that. In terms of format, Woojin will give a brief presentation. If you have questions, you'll notice there's a Q&A chat box down at the bottom. Please type your questions in the Q&A, and then as Woojin wraps up the formal portion of the presentation, we'll share those questions with Woojin and have them answered in order there. So Woojin, again, thank you very much for taking some time for our attendees today and for the webinar that we'll be hosting on the IEA website. But with that, I'll turn it over to you, and we can learn more about a mixed sensor smart chair system for real-time posture classification and chronic low back pain detection. So thank you very much.
Thank you, Stephen, for the kind introduction. Again, my name is Woojin Park. I'm a professor at Department of Industrial Engineering, Seoul National University, and I'm supervising Life Enhancing Technology Laboratory. I'm also the chair of Scientific Programming Committee for IEA 2024. So at the end of the presentation, as Steve mentioned, I'll be giving you some updates about the Congress. So the title of my presentation today is Mixed Sensor Smart Chair System for Real-Time Posture Classification and Chronic Low Back Pain Detection. So my presentation today consists of two parts. The first part will be concerned with the use of mixed sensor smart chair system for posture classification. And the second part is concerned with chronic low back pain detection utilizing the mixed sensor smart chair system. Okay, so the first part. As ergonomists, we are all aware that sitting postures, especially prolonged sitting postures, can be very hazardous to our health, especially maintaining awkward and stressful postures. So stressful postures can cause physical discomfort, and they are also associated with increased risks of WMSD. So much research has been conducted, and now we know what postures are more hazardous, like high risk, and what postures are relatively safer, and so on. So on this screen, I'm showing you a total of 11 sitting posture categories. And the literature in general suggests that the first two, like category 1 and 2, are relatively safer. And the other postures that are characterized by excessive flexion or excessive leaning, twisting, and also crossed legs and things like that. I mean, these postures are relatively more hazardous. So if possible, we should try to avoid these high-risk sitting postures as much as possible while working in a seated position. However, avoiding high-risk sitting postures in the middle of a primary task, like writing a research paper or working on a complex problem and things like that, is not exactly easy, because avoiding high-risk postures requires continually monitoring one's own posture and making corrections when necessary. And it's very difficult to do that while you're focusing on attention-demanding primary tasks. So a promising solution is to develop an aid, an external posture feedback or warning system, which does the monitoring and warning. So a system that continually monitors the worker's posture, detects the occurrence of a stressful posture, and provides a warning through an effective yet non-distracting display. And in order to create such feedback or warning system, we also need to create a subsystem that is capable of monitoring and classifying seated workers' postures in real time. So that's the motivation of this research study. In fact, I mean, there have been some previous researches on real-time sitting posture classification. And indeed, I mean, there were several. And these previous studies have proposed different systems, and they can be categorized into three types. So wearable systems, image-based systems, and the last one is pressure sensor embedded systems. In other words, smart chairs. So the wearable systems involve placing sensors like IMU sensors, or sometimes, I mean, they use optical fibers on the body surface, or sometimes a wearable system is actually clothes, I mean, with some embedded sensors. So these systems work, but they have the weakness of invasiveness and inconvenience. The image-based systems, they utilize cameras which capture a worker's postures real time. And using image classification algorithm, it's possible to classify a sitting posture real time. However, when the worker is occluded, right? And so if some objects occlude the camera, then this system doesn't work. And also, an image-based system has the weakness of psychological discomfort. Like many people find it very uncomfortable to be monitored by a camera in a room, right? So that's another like weakness of the image-based systems. And the third one, the smart chair, pressure sensor embedded systems, they do not have these weaknesses of wearable and image-based systems. By the way, a smart chair is an office chair with some sensors embedded on the seat pan, inside the seat pan. So a pressure pad or an array of pressure sensors is embedded into the seat cushion of a chair, and that is a smart chair. And smart chairs have shown some good performance, but their capability is limited in the sense that the pressure sensors on the seat cushion have some limited capability of like classifying postures. I mean, you can do only so much with pressure sensors embedded in the seat cushion. There is a limit to the range of posture categories that can be classified accurately. So, so the long-term goal of our research is to develop an effective real-time posture feedback system that contributes to reducing sitting-related discomfort and musculoskeletal problems. And the purpose of this study that I'm reporting today was to first, develop a novel, affordable, sensor-embedded smart chair system that is capable of monitoring and correctly classifying an instantaneous sitting posture as one of the major sitting posture categories discussed in the ergonomics literature, and two, empirically validate its posture classification performance. So to accomplish the research objectives to the current study and make some contributions to the body of knowledge, we adopted a new design strategy of combining a small set of distance sensors with also a small number of pressure sensors. So the uniqueness of our design approach is that we are using two different types of sensors in combination. So we call this approach a mixed sensor design approach. So Here's the list of predefined posture categories for the mixed sensor system. So what we wanted to accomplish is to create a mixed sensor smart chair system that is capable of classifying or differentiating the 11 posture categories shown on the slide. Okay, here's the physical description of the mixed sensor system. So the mixed sensor smart chair system that we developed is just an office chair, but it has a total of 12 sensors embedded in the seat back and seat cushion. So in the seat back area, as you can see, there are like 6 distance sensors, infrared distance sensors embedded in different places. And within the seat cushion area, there are 6 pressure sensors. Okay, so you can see the arrangement of the 6 pressure sensors on the seat cushion. So we are using the 2 different types of sensors in combination in order to improve the classification ability of the smart chair. In designing, in other words, in determining the positions of the 12 sensors, we actually referred to a Korean anthropometric data set, okay, known as Size Korea, so that the majority of the adult population can use this smart chair system. Okay, so the sensors that I described in the previous slides will provide some measurements in real time. And there is a machine learning based classifier, which on the basis of the sensor measurements classify an instantaneous posture as one of the 11 posture categories that I described earlier. And the classifier is indeed a k nearest neighbor classifier, okay, which is a popular method for classification in the domain of machine learning. So when using a KNN classifier, a test case, that is a new observation to be classified, is classified based on the classes of the k most similar cases, known as the k nearest neighbors, found in the training dataset. So the class of the test case is determined by a majority vote among the classes of the k nearest neighbors. So KNN classifier is a very simple method for classification, but it actually works pretty well in certain cases. So in order to develop this KNN-based classification system, we needed some training data set for model building, and also in order to test the performance of the smart chair system, we also needed some data for the testing purpose. So we conducted some data collection, and so basically, we recruited a total of 36 individuals and asked each individual to take the postures that I described earlier, the 11 posture categories, one by one. And for each posture, the participants were asked to maintain the posture for 10 seconds. So this way, we were able to collect, label the sensor measurement data, and this data set was utilized for training and also testing the KNN classifier. Okay, now the evaluation of posture classification performance. The posture classification performance of the mixed sensor system was evaluated in comparison with 2 benchmark systems, the pressure sensors only system and the distance sensors only system. So they are not based on this combination design approach, but each one of these 2 benchmark systems utilizes just one type of sensor. Okay, so basically we were interested in understanding whether this combinatory or combination approach of design enhances posture classification performance in comparison with the design approach of utilizing a single sensor type. For each of the three systems, I mean our system and two benchmark systems, the posture classifier performance was evaluated through tenfold cross-validation, which is a popular method for evaluating machine learning algorithms performance. And as measures of performance of classification, we utilized widely used measures, performance measures like overall accuracy, precision, recall, and F1 score. So here are some results from our analysis. So first, I'm presenting confusion matrices on this slide. So figure A and B represent the performance of classification for the two benchmark systems. So A for the pressure sensors only system, and B the distance sensors only system, and C represents the performance of the mixed sensor smart chair system that we developed. And basically, a perfect classification system would have ones in the diagonal and zeros in the off-diagonal positions. And the higher the number in the diagonal, I mean, the better the performance of classification is. So compared with the pressure sensors only system and the distance sensors only system, the mixed sensor system seems to perform a lot better. Okay. So across all the different posture categories, these numbers represent posture categories. So across the different posture categories we considered, the accuracy is pretty high, like 0.86 or higher for the mixed sensor smart sensor system. And we see many zeros and very low, small number in the off-diagonal positions. And the pressure sensors only system and the distance sensors only system are also doing more or less good. But then again, I mean, their performance is not as good as the mixed sensor system. Now, the multiple bar graph shows the F1 scores of the three systems in comparison for different posture categories. So across the different posture categories that we considered in this study, mixed sensor system was pretty much the best compared with the other two benchmark systems. And this also shows that the F1 score is very high for the mixed sensor system across the different posture categories. So it shows the robustness of the performance of the mixed sensor system. Okay, discussion. So the mixed sensor system was found to achieve a high overall posture classification accuracy. So the accuracy, the mean accuracy was 0.92. And the mixed sensor system was able to perform accurate classifications robustly across all of the posture categories considered. And the performance of the mixed sensor system was better than, or at least comparable to those of the benchmarks, excuse me, consistently across the posture categories considered. The excellent posture classification performance of our system is thought to result from the design approach that is combining the two types of sensors. Okay, so the distance sensors and pressure sensors instead of relying on only one type of sensors. And the proposed mixed sensor system is considered an improvement over the existing pressure sensor-based smart chair systems in that it enables a wider variety of ergonomically relevant sitting postures. economically using a small number of sensors. Okay, possible applications of the mixed sensor smart chair system. The mixed sensor system could be combined with a real-time feedback/warning system to help the users adjust their postures and thereby contribute to reducing the risks of WMSDs. So that was the motivation of this study at the start. And another possible application we are currently considering is estimating the seated workers' mental workload from conducting a cognitive task on the basis of real-time posture measurements. We have found some previous studies which reported that postural behavior sort of like reflects the cognitive demand or mental workload during a cognitive task. So we are currently hypothesizing that maybe by looking at seated workers' postural behavior, it may be possible to quantify the level of mental workload associated with cognitive task. So that's another possible application that we are considering at the moment. And the third one, the mixed sensor system may also be utilized for the diagnosis or prognosis of musculoskeletal conditions, like certain musculoskeletal conditions, for example, chronic low back pain. Let me check some message. Okay, Q&A. Okay, I'll address the question after I finish the presentation. Okay. Now, moving on to the second part of my presentation, chronic low back pain detection using the smart chair, the mixed sensor smart chair. So we extended the smart chair system, the mixed sensor smart chair system for posture classification to another system which is designed to detect chronic low back pain. Okay, so the system that we developed after the development of the posture classification system classifies a user, a seated worker, as either a chronic low back patient or a non-patient. Okay? And we all understand the significance of low back pain. So how does this smart chair-based low back pain recognition system work? The mixed sensor smart chair system that I described earlier is used to generate a time sequence of sitting postures while a user is performing a computer typing task for a 1 hour time period. So when a worker, comes to work, we just ask that person to conduct a typical computer typing task for 1 hour time period. And while the person is performing a typing task for 1 hour, the smart chair system will generate the sequence of postures or posture categories over time. Okay, because the smart chair system is capable of doing that. Okay? As I presented in my first part of presentation. Then another machine learning model based on the CAT-boost algorithm, category boost algorithm, classifies that person, that individual, either a CLBP patient or a non-patient, okay, on the basis of the posture time sequence generated by the mixed sensor smart chair system. That's how this so-called chronic low back pain detector works. So in performing the classification, a binary classification, a patient versus non-patient, the classifier utilizes a set of features, so relative frequencies of posture categories during the 1 hour time period. And time changes in relative frequencies of posture categories over that 1 hour time period. And the third one is the number of posture categories observed during the 1 hour time period. So this represents the variability of human posture during a time period. So our CLBP detector utilizes these features in order to perform the classification, the binary classification between patient versus non-patient. And here's the result for our current system. Okay, so we actually tried a number of different algorithms or modeling methods in order to develop this chronic low back pain recognition system. And the CAT boost, the category boosting algorithm, emerged as the best method so far. And here are the performance scores. So accuracy is 78.3%, and precision was very high. So 95%, and recall 76.6. And so the F1 score, which is the harmonic mean of precision and recall, is 81.3%. So this is not super accurate. It's not like over 95%, but I think personally that achieving this level of accuracy, like 81.3%, is pretty good, especially when considering that our research is probably the first attempt to detect chronic low back pain on the basis of sensor measurements from a chair. Okay. Right. So the mixed sensor smart chair system can be used for the diagnosis of chronic low back pain. It's able to differentiate between chronic low back pain patients and non-patients with high accuracy. And currently, we are hypothesizing that maybe the smart chair system may be capable of prognosis as well, in addition to making diagnosis. So if the smart chair system or the CLBP detector can be utilized for predicting the future occurrences and progresses of chronic low back pain, then it will be very useful in terms of controlling the incidence of chronic low back pain. That's actually what we'll be doing in the future, I think. And also, we think that in addition to low back pain, maybe other types of musculoskeletal symptoms or problems could be diagnosed with the mixed sensor smart system that I described today. So that's also another direction for future research. Okay, so I think I used about 30 minutes, am I right? So thank you for your attention. And should I talk about IEA 2024 now, or I mean, should I do that after I address some of the questions from the audience?
Sure. Let's do a couple questions first, Woojin, and then we'll turn it over to do a quick update on IEA, which is really exciting. So we have two questions here. Kailash, if you're still on the call, I think we've allowed you to talk, so you can unmute, and you're welcome to ask your question directly if you'd like.
Yeah, sure. Thank you very much. Yeah, my question was, what's the logic used behind the selection of these posture categories? And I think the second part of the question, I think you have touched on already, actually. So the second part was, how does these categories actually relate to the risk levels? So if you could add some insights to that, that'd be great. Thank you.
Okay, let me quickly go to that slide. Okay. So we considered a total of 11 posture categories for sitting posture. And in fact, I mean, we collected these posture categories from the literature, ergonomics literature on sitting-related musculoskeletal problems, which includes some standards. Okay, so I can provide. In fact, I mean, you can you can obtain the information about the references that we used for putting together this list of posture categories from our research article. By the way, oops. So I'm providing, excuse me, the reference. So the first one, which was already published in a journal. So somewhere in this article, I mean, you'll be able to identify the references that we referred to when creating the list of posture categories. And those previous studies, indeed, I mean, describe why the first two postures are relatively safer, and the rest are like high risk. Okay, so it's not like we decided that these should be posture categories off the top of our head, but rather the selection was based on the existing literature on sitting related musculoskeletal problems. Okay. Does this answer your question?
It does. Thank you very much.
And the second question, okay.
Yeah, Gunther, if you'd like to join us and ask your question directly to Woojin.
Sure. Thanks for the presentation. I hope you can hear me. Obviously, this approach has been considered before, and in the past, it's not been followed through because there appear to be issues with the measurement interfering significantly with the posture that was supposed to be measured. So posture, as we know, is highly dependent on seat comfort, and modifications of seat comfort will impact on posture. So if the measurement changes comfort, it will change the posture. So it can't change the natural posture because the posture becomes a function of the measurement. Now I'm wondering, because you've already progressed towards the prediction of physiological health outcomes, like low back pain. I'm wondering if we just keep a step back, if you've fully validated that the system does not interfere as we would expect from the technology, which obviously adds sensors into the seat back and the seat cushion, which normally would be expected to interfere with the measurement. So please tell us a bit more about your validation studies.
I mean, as I described in my presentation, our validation was focused on mostly prediction accuracy. So we did not really look at the possible interference with seat comfort or influencing posture. However, when we designed the smart chair system, in fact, these sensors were sort of like embedded into the seat back. Okay, so that there was no like protrusion on the surface of seat pan or seat back. So in terms of like the contact between the human body and these two elements, right, seat back and seat pan, there was no notable or noticeable discomfort associated with the embedding of these sensors. But I have to say that we have not really thought about the possible effect of these sensors on human discomfort perception. I mean, my expectation is that, I mean, it's probably negligible. And similarly, I don't really think, I mean, based on my own experience with this smart chair, I don't really think that the physical embedding of these sensors into the chair can change posture behavior. Okay. And of course, I mean, the warning system that I was talking about, the warning system which monitors the human posture, detects the occurrence of awkward postures and provides some warning if awkward postures are maintained for prolonged durations. I mean, the kind of system that's supposed to change postural behavior, I mean, to a better behavior. Okay. And that actually has been studied in another research study that my group has conducted so far. So we, in fact, created a visual display which shows the occurrence of awkward posture and presents that information in the peripheral vision of the human visual field so that you can deliver the information without distracting the worker who is in the middle of cognitive work. So that aspect has been studied, but so my current hypothesis is that because of the physical design of these sensors and their embedding, I don't think, I mean, this chair actually creates more discomfort, higher discomfort than a regular office chair. And also, I don't think, I mean, the physical characteristics of the current design influences postural behavior. But I mean, as I really appreciate the question. I mean, to be like more rigorous about our conclusion about this mixed sensor system, we should probably compare the postural behavior and also discomfort perception between the mixed sensor chair system and a regular office chair system, which does not have these sensors in it. And what was the other question? I'm sorry, I forgot the second part of your question, Gunther.
Was there a second part of your question?
Can you still hear me?
Yeah.
Okay, yeah.
Yeah, well, there wasn't really a second part, but it's the idea was before you progress into predicting certain health outcomes or health properties, because you kind of predict low back pain patient. So the idea was to just make sure that the system doesn't drive a certain posture that would then predict a low back pain patient. So in the worst case, you'd predict a large number of low back pain patients if the system has not been properly validated. So that might lead to the misperception of a state of health, which would be a bit risky, because that then drive cost in the health system and obviously cost in companies. So I think we'd have to be very careful with this.
Yeah, very good point. And in order to accurately determine the health benefits, or even, I mean, the opposite, I guess, I mean, of this particular system, we actually need to conduct a longitudinal study, okay, over a long period of time, so that if the use of this particular smart chair system can result in some health benefits, like reduced incidence of low back pain over some long period of time, like a couple of years or even longer, right? And that's actually something that we should do in the future, I think. I mean, in order to show the actual health benefits of this system. So I really appreciate your comment, and we'll try to conduct such a study. Okay.
Excellent. Thank you, Gunther, for the question, and thank you, Woojin, for the response there. There's one other question from Ramon. Ramon, I wondered if you wanted to join us and ask directly.
Mm.
May have some technical issues there, but I think the question, Woojin, was around.
Yeah, I can see the question, so I'll read it and then I'll try to answer. So hello, Ramona Basa. Hello. I noticed there is no sensor embedded on the headrest. The posterior of the head or skull, will this not be a big factor in determining the validity of the study? I mean, the study that I described today I don't think it has a validity issue. I mean, in terms of the study or the validity of the research study. And I think embedding some sensors in the headrest is actually an excellent design idea. So by adding more sensors in the headrest area, like inside the headrest, I mean, I'm not sure what kind of sensors would be the best for the headrest part, but I would think, I mean, adding some sensors to the headrest will provide additional information and therefore will improve prediction accuracy or classification accuracy of the system. And in addition to that, maybe adding more sensors to the headrest will improve the range of posture categories that can be classified with a system like this. So thank you very much for the comment, and I think you're providing a very good design idea indeed.
Excellent. Yeah, I can definitely, as I'm sitting here in my own chair and just thinking about head movement, I can see the value there. Woojin, thank you very much for your presentation, and just for the attendees and for those that might be following in the YouTube, recreation of this later. I hope that you could just share a brief update on the IEA 2024 Congress in Jeju Island for us.
Okay. So the website has been developed and it's up and running. So please visit www.iea2024.com or www.iea2024.org to get more information about the Congress. And I'm just giving you some information about the Congress here. So it's the 22nd Triennial Congress of the International Ergonomics Association. And this time, the conference will be held in Jeju Island, South Korea. Jeju Island is a volcanic island, very beautiful, and it's considered like Hawaii for the United States. So it's very beautiful, and it has like a lot of things to do. So please come to Jeju Island next year. And we expect to see about 1,500 or even more participants, delegates from around the world for IEA 2024. And one thing unique about IEA 2024 is that it's going to be the very first hybrid conference. Before 2021, the IEA 2021, which was held in Vancouver, all IEA triennial congresses have been in person. Okay, and IEA 2021 was the first all virtual Congress. And this time, IEA 2024 in Korea will be the very first hybrid conference. So the participants, the presenters will be able to present in person or virtually, and also audience will be able to participate virtually or in person. So that's the idea. And the Congress will be held from August 25th to 29th, 2024. And as I mentioned earlier, for more information, please visit this website, and you can make submission at the moment. Of some important dates, proposal submission round 1 and 2. We have 2 rounds of proposal submission because like some people wanted to submit their presentation proposals somewhat early, I mean, for the internal approval from their organization and also budget planning and things like that. So the first round will be from September 15th to October 31st. And the second round will be from November 1st to February 29th. And full paper submission is optional, and the time period for full paper submission will be from January 1st to April 15th. Okay. Full papers, if accepted, will be published in conference proceedings, Springer books. So that's also, I guess, important information for those who are considering. And what else? Well, I mean, the website currently has some room for improvement, and we are making every effort to improve it. But it's functioning, so you can actually submit your presentation proposals at the moment and get important information from the website. And I very much hope that many people will come to Jeju Island next year, and we can have some excellent academic exchange next year in Korea. Okay.
Woojin, thank you for those details. I know I'm looking forward to being in Jeju for the IEA Congress next August. For any of you on the MSD or involved in the MSD Technical Committee, we'd love to have a number of papers at the conference to share and discuss MSD prevention strategies and ideas as well. It'd be great to have a strong presence from our MSD technical group. But Woojin, with that, thank you so much for taking some time out of your schedule to share your really interesting research with us. And for those that were able to join the call live and had some really exciting questions, Woojin, I'm sure you'll get lots more questions from folks that watch this presentation online once we get that posted as well. So thank you so much. And I do look forward to seeing you in person next year in Jeju.
Okay. Once again, thanks for this invitation, and it has been a great pleasure for me. And I hope to see you all in Jeju next year. Thank you.
Sounds great. Thank you, everyone.
Bye.
Thanks, Woojin.